Hello and welcome. In this tutorial from Math Zone African Motives, we'll be starting our study of functions and graphs. Our main goal today is to introduce the fundamental concepts that form the basis of all graph analysis. By the end of this session, you will be able to define key terms like graph, origin, and ordered pair. You'll also learn to locate points on the Cartesian plane and identify its four quadrants. This will provide you with a solid foundation for more complex topics. So what is a graph? A graph is a visual representation, a picture, of the relationship between two variables in an equation. We can see this relationship by plotting points that satisfy the equation on a special coordinate system. The system we use is called the Cartesian plane. Think of it as a grid that helps us map numbers to positions. The Cartesian plane is formed by two perpendicular number lines, one horizontal called the x-axis and one vertical called the y-axis. The point where these two axes meet, at 0 on both number lines, is very important. It's called the origin. So the origin is located at the coordinates 0, 0. It's the central reference point for the entire plane. The intersection of the x-axis and the y-axis divides the Cartesian plane into four regions, which we call quadrants. Quadrant 1 is the top right section, where both the x and y coordinates are positive. Quadrant 2 is the top left, where x values are negative and y values are positive. Quadrant 3 is the bottom left, where both x and y coordinates are negative. And finally, Quadrant 4 is the bottom right, with positive x values and negative y values. In this scene, we've defined what a graph and the Cartesian plane are, located the origin, and identified the four quadrants. This is the coordinate system we'll be using to draw all of our graphs. Now that we have our plane, how do we find any point on it? We use what's called an ordered pair. An ordered pair is a set of two values that tells us a point's exact location. It's written in the form xy, where the first value is the x-coordinate and the second is the y-coordinate. The order matters, which is why we call it an ordered pair. Let's look at figure 4.2. We have a Cartesian plane and a point labeled A. The coordinates of point A are r3, 2. This ordered pair tells us how to get to point A from the origin 0, 0. The x-coordinate is 3. This means we move 3 units horizontally from the origin. Because it's negative, we move 3 units to the left along the x-axis. From there, we look at the y-coordinate, which is positive 2. So, we move 2 units vertically upwards, parallel to the y-axis. And there we are, at point A with coordinates r3, 2. Point A is located in quadrant 2, as we expect for a point with a negative x value and a positive y value. In this scene, we've learned to use ordered pairs to describe and find any point on the Cartesian plane. We saw that the first number tells us the horizontal position and the second number tells us the vertical position. You can now use coordinates to navigate this coordinate system. Next, let's explore two more fundamental concepts for describing graphs: the domain and the range. First, the domain. The domain represents all the possible input values for an equation, which we typically call x-values. So it's the set of all the x-coordinates that exist on a graph. Second, the range. The range is the set of all the possible output values, or y-values, that an equation can produce. In other words, the range is the set of all the y-coordinates on a graph. To recap, the domain is the horizontal extent of the graph on the x-axis, and the range is its vertical extent on the y-axis. Let's apply these definitions to an example. Consider figure 4.3, a straight line graph. The graph is a line segment drawn from a specific set of points. If we were to list the x values from this set, we'd get our initial domain. If we list the y values, we'd get our initial range. So the domain is negative 1.5, negative 0.5, 0, 1, 2, and 3. The range is negative 1, 0, 0.5, 1.5, 2.5, and 3.5. However, this is only part of the story. The graph is a solid line, which means it includes every single point between those endpoints. This means the domain and range contain infinitely many points, not just the ones we started with. To describe these infinite sets, we use inequalities and set builder notation. Let's find the true domain. First, we look at the x-axis. The graph starts at x equals negative 1.5 and ends at x equals 3. Every point on the line has an x-coordinate between these two values. We can write this as an inequality. x is greater than or equal to negative 1.5, and x is less than or equal to 3. The notation means the set of all x values such that x is between negative 1.5 and 3 inclusive. Because it's a solid line, these x values can be any real number. Now let's find the true range. Similarly, we look at the y-axis. The graph's lowest point is at y equals negative 1, and its highest point is at y equals 3.5. All y-coordinates lie in this interval. We write this as y is greater than or equal to negative 1, and y is less than or equal to 3.5. And again, because it's a solid line, these y values can be any real number. So, the range is the set of all real y values between negative 1 and 3.5, inclusive. Let's pause here. The provided memo for this example gives the correct final domain and range. But the initial point-based lists are a helpful stepping stone to understand why the interval notation is necessary for a continuous graph. In this scene, we've learned the definitions of domain and range and saw how to identify them, first from a set of points, and then, more accurately, from a continuous line segment. You can now determine the domain and range of a simple graph. Our next topic is one of the most important in algebra: the distinction between relations and functions. A relation is any equation or set of ordered pairs showing a mathematical connection between two quantities. A function is a special type of relation. It's a rule that assigns exactly one output value to each input value. In other words, for every x value you put in, you get only one y value out. This one-on-one mapping is the key difference. Think of a function like a machine. You put one thing in and you always get the same one thing out. To determine whether a graph is a function or just a relation, we can use a simple visual test. This is known as the vertical line test. We draw vertical lines across the graph and observe how many times they intersect it. Let's apply this to figure 4.4. First, let's look at the graph labeled A. If we draw a vertical line through this ellipse, notice it cuts the graph at two different points. This means that for the single x value of that line, there are two corresponding y values on the graph. This violates the definition of a function. So, because the vertical line intersects the ellipse more than once, the ellipse represents a relation but not a function. Now let's apply the vertical line test to the second graph, labeled B. No matter where we draw a vertical line through this parabola, it will only ever intersect the graph at exactly one point. This tells us that for every x value, there is only one unique y value. This perfectly matches the definition of a function. Therefore, this parabola represents a function. The key takeaway is the vertical line test. In this scene, we've distinguished between relations and functions and learned the vertical line test. This is a powerful tool to quickly determine if any graph represents a function. The main point is that a function can't have one x value producing multiple y values. Let's continue by looking at the roles of variables in an equation. This brings us to the concepts of dependent and independent variables. First, we have an independent variable. Its value is chosen freely. It does not depend on anything else in the equation. Think of it as the input. It's the variable we can control or set. Conversely, a dependent variable is one whose value is determined by or depends on the value of the independent variable. It's the output. Its value is a result of the independent variable's value. Let's look at an example, the equation y equals pi x squared plus 3x minus 4. In this equation, pi, 3, and 4 are constants. They have fixed values. The letters x and y are the variables, meaning their values can change. If we choose a value for x, we perform some calculations, and we get a value for y. So, the value of y is entirely determined by the value we choose for x. This makes y the dependent variable, and x the independent variable. Since y is dependent on x, we can say y is a function of x. This is often written in function notation as y ishi atha fx. This notation fx simply means the dependent variable, or the value of the function, depends on x. Now let's see this in action with an example. We are given the function y equals 4 god 7. The question asks us to find the values of f0, f1, f2, fa plus b, and f of the quantity 3 plus a all over 4. First, we translate the equation into function notation. Since y depends on x, we can write fx equals 4 given 7. Now let's solve each part one by one. For f0, we substitute 0 for x, so we have 4 times 0 minus 7, which equals negative 7. For f auto 1, we substitute 1 for x. That's 4 times 1, which is 4, and 4 minus 7 is 11. For f auto 2, we substitute 2 for x. That's 4 times 2, which is 8, and 8 minus 7 is 1. This one is a bit different. For f a plus b, we substitute the entire expression a plus b for x. We get 4 times the quantity, a plus b, minus 7. Using the distributive property, this becomes 4a plus 4b minus 7. Finally, for f of the quantity, I3 + 4, we substitute this fraction for x. So we have 4 times the fraction, minus 7. Notice the 4 in the numerator and denominator cancel out, leaving us with 3 plus a minus 7. Simplifying this gives our final answer, a minus 4. A quick check against the provided memo shows a slight discrepancy for this last answer, which is given as 4 plus a. As we've shown, our result, a equals 4, is algebraically equivalent and therefore correct. Both represent the same answer. In this scene, we've defined and distinguished between dependent and independent variables. We then saw how this leads to function notation and practiced evaluating functions for various inputs. The key idea is that the dependent variable's value is the output of the function, and it depends on the independent variable's input. Let's move on to inverse functions and relations. The idea here is to reverse or undo a function. Inverse functions are functions that reverse the effect of each other. If a function takes an input x and gives an output y, its inverse will take that y and return the original x. The notation for the inverse of a function f(x) is f inverse of x. The graphical relationship between a function and its inverse is beautiful. They are reflections of each other over the line. E equal x. Imagine the line y equals x as a mirror. The graph of a function and the graph of its inverse would be mirror images on opposite sides of this line. This happens because the domain of one becomes the range of the other and vice versa. There's an important condition for an equation to have an inverse that is also a function. It must pass the horizontal line test. The horizontal line test is just like the vertical line test, but we draw horizontal lines. If any horizontal line intersects the graph more than once, its inverse will not be a function. Its inverse will be a relation, because it would fail the vertical line test. Let's use a function where f(x) equals y. The core principle of finding its inverse is simple. You interchange the roles of x and y. After swapping them, your new equation will be x equals some expression in terms of y. Your next step is to rearrange that equation to solve for y. This new expression for y will be your inverse function, finverse of x. Let's go through some examples to solidify this process. Our task is to find the inverse of 3 different functions. First, for the linear function y else 3 plus 2, the first step is to interchange x and y. This gives us x will equal to 3 plus 2. Now we make y the subject of this equation. First, we subtract 2 from both sides. So 3 al x 2. Then we divide both sides by 3 to get y equal x or 2, 3. This is our inverse function. We write it using the correct notation. F inverse of x equals the quantity, x plus 2 over 3. Now let's find the inverse of the logarithmic function y equals log base a of x. Swapping x and y gives x equals log base a of y. To solve for y, we need to convert this logarithmic equation into an exponential equation. Remember the rule for logarithms. Log base b of c equals d is equivalent to b raised to the power of d equals c. Applying this rule, our equation x equals log base a of y becomes y equals a raised to the power of x. So the inverse of log base a of x is a raised to the power of x. This is an important relationship to remember. Logarithms and exponentials are inverses of each other. Finally, let's find the inverse of y equals ln x. The natural logarithm, ln x, is just a specific type of logarithm, where the base a is the mathematical constant e. So our equation is x equals log base e of y. We follow the exact same process. Convert this logarithmic form to exponential form. The base is e, the exponent is x, and the result is y. So y equals e to the power of x. The inverse of the natural logarithm, ln x, is the natural exponential e to the power of x. The memo confirms all 3 of these inverses are correct. In this scene, we've defined inverse functions as tools to reverse each other. We learned the horizontal line test to check if an inverse is also a function. Most importantly, we mastered the two-step process to find an inverse. Swap x and y, and then solve for y. You can now calculate the inverse for various types of functions. Our next topic is about the flow of a graph. Are there any breaks or gaps? This leads us to the concepts of continuous and discontinuous graphs. We'll define continuous as without interruption and discontinuous as having gaps. A continuous function or relation is one whose graph can be drawn completely in one smooth motion without lifting your pencil from the paper. There are no holes, jumps, or asymptotes. Figure 4.6 gives several examples. A perfectly smooth curve like an ellipse is continuous. A parabola is continuous. Even the graph of y equals x cubed, which goes on forever, is continuous. You can draw each of them in one continuous stroke. On the other hand, a discontinuous function or relation is one whose graph you cannot draw without lifting your pencil. It has interruptions, or breaks. Figure 4.7 illustrates this perfectly. Look at the hyperbola in the first quadrant. It approaches the x and y axes but never touches them. Then there's a complete break, and a separate branch appears in the third quadrant. You have to lift your pencil to draw the second branch. This type of break is often caused by an asymptote. An asymptote is a line that the curve gets closer and closer to, but never actually reaches. Here, the x-axis and y-axis are asymptotes. This graph is discontinuous. Let's look at another example of discontinuity from figure 4.7. This graph shows the function y equals tan x. It has multiple branches, each separated by a dashed vertical line. These vertical lines are asymptotes, where the function's value goes to infinity. Since there are these infinite breaks, the tangent function is discontinuous. There are many types of discontinuities, but for now, remember this simple visual test. Can you draw it without lifting your pencil? If yes, it's continuous. If no, it's discontinuous. In this scene, we've learned to distinguish between continuous and discontinuous graphs. A continuous graph is smooth with no breaks, while a discontinuous graph has gaps. You can now identify if a graph is continuous or not by using the pencil test. Our final topic for this introductory unit is symmetry. Symmetry is a beautiful property of many mathematical figures and graphs. It's all about balanced proportions and mirror images. First, let's define an axis of symmetry. This is a straight line that divides a graph into two identical halves that are mirror images of each other. Think of it like folding a piece of paper. If you can fold a graph along a line and the two halves match up perfectly, that fold line is an axis of symmetry. Figure 4.8 gives us three examples of axes of symmetry. In graph A, we have a parabola opening to the right. The text says it's symmetrical about the x-axis. Let's see why. The x-axis is a horizontal line. If you were to fold this graph along the x-axis, the top half of the parabola would land perfectly on the bottom half. Therefore, the x-axis is the axis of symmetry. In graph BB, we have a parabola opening upwards. The text states it's symmetrical about the y-axis. Here, the y-axis is a vertical line. If you fold the graph along this line, the right side would perfectly match the left side. The y-axis is the axis of symmetry. Let's pause and note that the memo text on the next page, referring to graph A and C, seems to be referencing diagrams from earlier in the module that are not included here. We will focus on the diagrams and definitions provided on this page. Now let's examine graph C. This hyperbola is a bit different. Can we find an axis of symmetry by folding? In graph C, the graph is not symmetrical about the x-axis or the y-axis. Folding it would not make the halves match. Instead, it has a different kind of symmetry. This graph has point symmetry, also called central symmetry, about the origin, 0, A point of symmetry is a special center point. A figure has point symmetry if it looks the same when rotated 180 degrees about that point. For this hyperbola, if you rotate the entire plane 180 degrees around the origin, the branch in quadrant 1 would land exactly on the branch in quadrant 3. It's symmetrical about the point, 0, We also see two other lines in graph, C, y-axis on x, and yx. These are not axes of symmetry, but they are another type of asymptotic behavior related to the lines that the branches of the hyperbola approach. In this scene, we've introduced the concept of symmetry and defined an axis of symmetry. We saw how to visually test for symmetry across the x-axis and y-axis. We also learned about point symmetry, where a graph is symmetrical about a central point. These symmetries help us to understand and sketch graphs more efficiently. Let's revisit the first page with Figure 4.8. The accompanying text gives several examples of symmetry. Let's read through these. Remember, we don't have graphs A, B, or C in this specific document, so we'll focus on the descriptions for those. First, the text defines two key terms. It mentions a point of symmetry. This is the same as the center point for rotation we discussed earlier. It also defines equidistant as meaning the same distance from something. We'll use this idea to analyze symmetry more deeply. Graph D is an ellipse. The text confirms it's symmetrical about both the x-axis and the y-axis. If we folded this ellipse along the x-axis, the top and bottom halves would match. If we folded it along the y-axis, the left and right halves would match. This confirms both axes are axes of symmetry. Graph E is a parabola. The text says it's symmetrical about a line parallel to the y-axis. Visually, we can see this axis of symmetry passes through the vertex of the parabola. This vertical line acts as the mirror. The memo then goes on to discuss graphs A and C, which we don't have visual access to. Let's analyze the descriptions given and see if we can understand the principles. The text for graph A says the points AB and HEB are points of symmetry as they are equidistant from the x-axis. A point is not an axis of symmetry. Let's correct this. A more precise statement would be that these 2 points demonstrate that graph A is symmetrical about the x-axis. Let's plot these 2 points on a graph. The point AB would have some x value A and a y value B. The point AB would have the same x value A, but a negative y value B. Since their x coordinates are identical and their y coordinates are opposites, these 2 points are located at the same horizontal position but at equal distances above and below the x-axis. They are equidistant from the x-axis, just as the text says. This pair of points is characteristic of a graph that has the x-axis as its axis of symmetry. The text correctly identifies the equidistant property, even if it labels them as points of symmetry rather than points demonstrating x-axis symmetry. Next, the memo mentions graph C. The 2 graphs are equidistant from the origin and the line drawn through the origin. This sounds like it's describing the symmetry of a hyperbola like the one in Figure 4.8. C. We saw that graph C has point symmetry about the origin. If a point is on one branch of a hyperbola, say in quadrant 1, the point directly across the origin in quadrant 3 is also on the graph. The distance from the origin to each of these points is the same. They are equidistant from the origin. The line drawn through the origin likely refers to the asymptotes, the lines y, h, x, and y, x that the hyperbola approaches. The branches of the hyperbola are not equidistant from these lines in a simple sense, but their shape is defined by their relationship to these asymptotes. In this scene, we've reviewed the various types of symmetry discussed. We confirmed that graph D is symmetrical about the x and y axes, and graph E has a vertical axis of symmetry. We also clarified the memo's text by understanding how specific points on a graph, or the shape of the graph itself, demonstrate symmetry, particularly in relation to the x-axis and the origin. Let's summarize what we've learned today. We started with the fundamentals of graphing. We defined the Cartesian plane, with its perpendicular x and y axes intersecting at the origin. We saw how to locate any point using an ordered pair x, y, and how these axes divide the plane into 4 quadrants. Next, we learned to describe the extent of a graph using its domain and range. The domain is the set of all possible x values, the horizontal spread. The range is the set of all possible y values, the vertical spread. We then moved on to functions, a special type of relation. We learned that a function has exactly one output for every input, and we used the vertical line test to identify them graphically. We also saw how independent and dependent variables are related in an equation. After that, we explored inverse functions. We defined them as operations that undo each other and learned how to find them by interchanging x and y and solving for the new y. We also introduced the horizontal line test for checking if an inverse is a function. Finally, we covered the visual characteristics of graphs. We learned that a continuous graph has no breaks, while a discontinuous graph does. And we identified different types of symmetry, like symmetry about an axis or a point, which help us understand the balance and structure of a graph. We've laid a strong foundation for understanding functions and graphs. Each of these concepts is a building block for the more complex functions you'll encounter next. By mastering these definitions and techniques, you've equipped yourself with the essential tools for graph analysis. Thank you for watching this tutorial from Math Zone African Motives. If you found this video helpful, please subscribe to our channel for more math tutorials. See you in the next video. Subscribe for more tutorials from Math Zone African Motives. Let's start with some definitions. A point of symmetry is a special center point for certain kinds of symmetric figures or graphs. Equidistant means the same distance from something. Figure 4.8 shows examples of symmetry. Graph D is an ellipse centered at the origin. Graph E is a parabola with a vertical axis of symmetry. Now let's refer to figure 4.8 to discuss different types of symmetry. Graph D is symmetrical about the x-axis and the y-axis. The same would apply if graph D were a circle. Graph E is symmetrical about a line parallel to the y-axis. In graph A, the 2 points, AB and AB, are points of symmetry, as they are equidistant from the x-axis. In graph C, the 2 graphs are equidistant from the origin and the line drawn through the origin.